Question 1 is about ionization energies, and it tells us for this set of sequential trends that the open squares relate to boron. Okay, so we know that these ones relate to boron, and what you're hopefully used to is the idea that you get 3 relatively easy ones because boron's in group 3. Okay, so 3 electrons in its outer shell. These first 3 ionizations are those being removed. And then the 4th one is hard because once the outer shell is gone, the next one has to go from the next shell down, so it's closer to the nucleus, it's less shielded from the nucleus, so much more strongly attracted, and that's why you get the big jump. So the unknown one, which is the circles here, you can see that that must be in group 2, because you've got 2 easy ones and then the big jump. So we can narrow it down straight away to a group 2 element, which means either A, beryllium, or B, magnesium. So the question is, which one is it? Don't just jump at the fact that you see a group 2 element straight away, because these are both group 2 elements. So to decide which one it is, you have to think about the other trends, and in particular we've got to relate it to boron. So if we think about the trend across a series, remember it goes like this. So you go group 1, goes up to group 2, and then it dips down again as you change from removing an s electron to removing a p electron, because the p electrons have slightly higher energy already, they're slightly easier to remove. So group 3 goes down again, and then it goes up and up as we start to eat away the p electrons until we get to group 6, and then suddenly we start removing paired p electrons instead of unpaired ones, so we get another blip, and that's the overall trend. So in period 2, that's going to be lithium, beryllium, boron, and so on. And the important thing about that is that you can see that beryllium should be higher than boron for its first ionization energy, but our group 2 element is lower than boron, so it can't be beryllium. As you go down a group, the first ionization energies decrease, so it could be magnesium. So B is the answer. Question 2 gives us this as the formula for iron 3 pyrophosphate, and it asks us to work out what the formula of the parent acid is, pyrophosphoric acid. So the point is that we know that the ion is 3+, right? So we know that we've got 4 lots of 3+ equals 12+, and therefore the negative ions must add up to 12-, so that the charges balance out overall. So we must have 3 lots of 4-, because we've got 3 pyrophosphate ions, so they must be 4- each to give you 12-, and that will balance the charges out overall. So we know therefore we've got P2O7 4- is the negative ion, so the acid that it's formed from just balances up those charges with H+ ions. So the answer is going to be that we have H+ 4 times, so 4 lots of H+ balances the 4- on there. So the formula of the acid is H4P2O7, which means the answer is C. Question 3 gives us this information, that we have a particle that has 115 neutrons, 74 electrons, and it's a 3+ ion, and we have to identify which isotope it is. This one actually is very easy. We don't really need all the detailed information that's there. The crucial thing is just to focus on that. If it's got 74 electrons and it's a 3+ ion, that means that if it was an atom, it would have 3 more electrons than that. Okay, because 3+ means it's lost 3 electrons. So the atom would have 74 plus 3 is 77 electrons. And of course, if it has 77 electrons, it must have 77 protons in order to balance up the charges. So we can just find the element whose atomic number is 77, and the answer is iridium. And then if we'd been given a choice of iridium isotopes, we'd have had to work out which one it was by using the neutrons, but in fact there was only one iridium isotope, so it has to be that one, which means the answer is C. Question 4 is about the relationship between the rate equation, which it tells us is this, and the rate determining step in a reaction. So the key thing you have to remember in all these kind of mechanism questions is that the order of reaction for each substance is equal to the number of particles of that substance involved in the rate determining step. So you can see in this case, if step 1 was the slow step, it would be the rate determining one, and in that case it would involve one ethene and one HBr, and therefore it would be first order for each, which is what we have. So that's a possible answer. It could be that the first step is the slow step. But we have to consider what happens if the second step is the slow step. So what happens if it's this way round? First step fast, second step slow. When you get that situation, what we learned was that what you have to do is then add up the steps up to and including the slow step. So if there was more than one in front, you'd add all of them up to and including the slow step, because the effective rate determining step then is the sum of those steps. And obviously if we add these two steps together, we just get the overall reaction equation. You can see that because these two ions which are formed here cancel out when we add them up, because they're there on the left hand side as well, and so our overall equation is just the reaction equation, which is this. So if this were true and the second step was the slow step, then we would have to say that the effective rate determining step is the sum of the two, which is that, and again it just has one ethene and one HBr, so it would give the same rate equation. So the answer is we can't tell which is true, and therefore the right answer is D. Question 5 is about thin layer chromatography, and it's asking us about the migration of this compound. I've just drawn it out there so you can see it more clearly on the TLC plate, and it's just saying if we made the mobile phase, which is the solvent, if we made that more polar, what difference would it make to the mobility and therefore to the RF value? So remember, mobility in TLC is about a competition between adsorption to the plate, which is tending to slow down migration, and dissolving in the stationary phase, which is what carries it up the plate. So if we're keeping the plate the same, which is what it tells us in the question, we don't have to think about that. We just have to think what happens if we make the solvent more polar, the mobile phase more polar. And you can see that this is a very polar compound. All these OH groups can form hydrogen bonds. You've got a polar carbonyl group as well. So this is a very polar substance. So if you make the solvent more polar, it's going to dissolve better in it. You know, that's the way it works, because a polar solvent's going to be able to form the hydrogen bonds and what have you to make this able to form a better set of intermolecular forces in solution. So the answer is this is going to be more soluble in a polar solvent, and that's going to make it less inclined to adsorb to the plate, so it will move faster, and therefore the RF value will be greater, which means that the answer is A for this question. Question 6 is about the evidence for aromaticity, the evidence that there's something special about benzene, which means it isn't just a normal alkene. And this is something you explicitly have to know about. So if you couldn't do this question, it's a sign that you need to revise that chunk of the aromatic chemistry module, that you need to be able to explain about the evidence for aromatic rings being special. So in this experiment, the idea was that they measured the enthalpy change when hydrogen is added to cyclohexene, and it gave you in the question the value for that as minus 120 kilojoules per mole. So that's the reaction. And the idea is that if benzene were not delocalized, if it was just 3 normal localized double bonds in a benzene ring, that you could approximate the value for delta H when that is hydrogenated by saying, well, it will just be 3 times as big. So we could predict that if we had 3 localized double bonds, as we draw in the Kekulé structure, if that reacted with 3H2, it would just be doing that same thing 3 times, and so we would then predict that delta H would be 3 times minus 120, which is minus 360 kilojoules per mole. And it's asking us, given that we know that that's not really what benzene is like, what difference does that make? So the point is that delocalization lowers the energy of the electrons. It puts them into a more stable state, which means a more, a lower energy state. So in other words, this is taken to a lower energy state as a result of delocalization. So if we now add hydrogen to it, we're going from this lower energy state down to the same product, because it still ends up as cyclohexane. And so delta H, as you can see, is going to be much less negative than the minus 360 that we predicted, because of the stabilization that the delocalization gives. And therefore the answer is B. Question 7, we've got to identify compound X based on this pattern of reactivity, and these are the options. So the first bit of information is that it doesn't react with nitric acid in aqueous solution, and in the context of these tests for ions, what that particularly tells us is that it's not a carbonate, because remember, it would fizz if it was a carbonate. Now none of these is a carbonate, so that doesn't tell us anything directly, but it's important because we need to know that information in order to interpret one of the tests that comes later on. Second bit of information is that there's no reaction with aqueous sodium hydroxide. Now that is important from the in the context of these possibilities, because remember, if you have an ammonium salt, if you have NH4+, and you react with sodium hydroxide, you get ammonia formed, because this reaction happens, and the ammonia gas is detectable because it smells, but also it turns red litmus paper to blue if it's damp. So the fact that there's no reaction with aqueous ammonia when you heat it tells us this is not an ammonium compound. So it straight away rules out C and it rules out D. So we're just now distinguishing between these two. So the one positive thing that it does do is it tells us that we get a white precipitate with barium nitrate. Now that could have been a carbonate because barium carbonate is insoluble, but we've excluded that. That's why we always do the acid test first to say, well, is it a carbonate or not? No, it isn't. So if it's not a carbonate but it does give a precipitate, it means it's a sulfate. So looking at these two, it's got to be that one. That one would not react because barium chloride is soluble, but barium sulfate is insoluble, so you get this reaction that the aqueous barium 2+ from the barium nitrate meets the aqueous sulfate from the potassium sulfate, and you get solid barium sulfate forming. So that's the sulfate test which you need to know, and therefore the answer is B.